Well, good evening, everybody. Let me first thank you for the invitation. I've been in the Bay Area for 30 years, so it's my first time here. So I consider this a true accomplishment. And so, my name is Robert Kostecki. I work at Lawrence Berkeley National Lab. I wear two hats over there. One is I'm a senior scientist, and I'm doing my own research with my research group. I'm also one of the division directors, leading the division of 200 people with approximately $44 million research project every year. When I came to the States here, with no intention of staying, like many of us, I graduated from Warsaw Technical University and then did my PhD at the University of Geneva in Switzerland. I'm here for a postdoc with no intention of staying, and here I am. Today, I would like to spend a little bit of time and present more of a perspective on the battery technology and what happened from early days of battery technology development, and then present you a sort of a broader picture of where we're going with that, and then what are the key challenges and tasks ahead of us. I'm not going to dive deep into any technicalities of the systems. I think that maybe we want to cover some of that. But I will sort of hint you on some of the key challenges that we have been busy with and working on in the past few decades. Now, when you look at the picture here, Lawrence Berkeley I would like to say a few words about the place that I work in. Lawrence Berkeley Lab is the oldest and one of the 17 national labs in the US. It is the Office of Science Lab, which focuses on fundamental challenges in science and technology. Historically, if you look at this photograph from 1939, and if you watch the movie Oppenheimer, you can find the guy over there. He's on the upper row, sitting on the top of the 60-inch cyclotron that's being constructed over there. And Lawrence received a Nobel Prize for this invention soon after, and that magnet is still at LBML today. So the lab has started 90 years ago as a nuclear sciences lab. It was part of the Manhattan Project. Here, all those names that you see on the right are people who participated in it. But over time, it evolved and included different disciplines and areas of science, like biosciences, energy sciences, and so on and so forth. So received 16 Nobel Prizes, and today's budget is $1.2 billion per year. That's the research budget that we know currently. It's arguable whether this is the best of all national labs in the country, but without a doubt, this is the lab with the best view. So if you come to visit us and you look at the bay, it's absolutely breathtaking. So this is what I would like to start talking about today. When all this story has started, and you have to go back to the end of the 19th century with the invention of Thomas Edison, electric lamp, which basically stimulated the development of electric grid and all electrical applications at the time, and basically started the second industrial revolution that was related to electrification and electricity that's being provided, to both industry as well as private users. So soon after, the grid, and the infrastructure started growing, and it hasn't changed much since those times. And Edison was definitely one of the key players together with Tesla at the time, developing, those early concepts of how the electrical infrastructure should look like, and that model had been copied and transplanted all around the world. Now, back there, when Edison was asked about batteries, that is what he said. It's below. It's not worth even looking at it. It's just a cheat. A method of cheating to the investors and trying to get some money from them, but it has absolutely no future. And that was in 1883. And then, as in many great minds, he has changed his mind. And the reason why he has changed his mind was that he realized that electricity and the part of the business that he owned, could be used in transportation through electric cars and batteries. And that is front cover of Scientific American from 1911 shows Edison himself, much older now, right next to an electric car that was equipped with the battery that he invented, a nickel iron battery at the time, which was, competitive to lead acid that, preceded it. In many ways, it was a better battery, not necessarily cheaper. But the truth is, if you read the paper, is that 1911, electric cars were the most preferred cars in the US. You wouldn't believe that. And the average range of electric car at that time was 144 miles.
Wow.
So a typical test, and we are talking 1911, the typical test was to drive from Manhattan all the way to the end of Long Island and back on one charge.
So why the most popular electric car is called
Well,
Tesla and not Edison?
There's a lot of them. So all cabs in New York City were electric. You know that? And then most of heavy loaders did. So we used to live in, well, not we, but people used to live in a better world a long time ago. What happened is the question that by 2020, all electric cars disappeared from the market. And basically, it was the end of story. This is a lesson. If somebody who thinks about batteries and electrification transportation today has to do the homework on the lessons that have been learned, a long, long time ago, 100 years ago. And this is what happened. That's what killed the electric car. The three primary reasons was the first one, very much like 1 year after what I showed you in 1912, they stopped manufacturing internal combustion engine vehicles equipped with lead acid battery and electric starter. Before that, this was how people had to start electric cars, combustion engine cars. You had to crank them. There's a lot of accidents, broken limbs, and that was not exactly a user-friendly way of using cars. The other one was another year after, it was Ford assembly line. And he picked, internal combustion engine-based car, Ford T, and that basically outpaced, competed everybody else in the market. The one unresolved problems at that time was that gasoline was expensive. This was not the cheap fuel, and that, caused all ICE-based cars, incur some quite significant costs. And it was this guy, Thomas Midgley Jr. from General Motors in 1921, that he found that tetraethyl lead additive to gasoline eliminates the knocking problem in internal combustion engine and also lowers and can make crappy fuel usable. And that increased the profit of car companies, oil companies, and basically all infrastructure started developing so fast that there was not even a slightest thought at the time of coming back to electric cars. Those were the key factors that basically swayed the market, and then everything else from then we know what happened. Now, what were the consequences of this? Well, I jumped too quick. I missed one slide.
That's fine.
One slide that is missing here. Well, anyways, tetraethyl lead is a lead-containing compound. And there was this one guy, Cameron Patterson. How many of you have heard of Cameron Patterson? He was from here. He was also, his pictures are down below. He was a nuclear physicist, who played part of the Manhattan Project. And he was the first guy who determined the Earth of the planet Earth, for 4.55 billion years. And he calculated that by looking at the isotope ratios from on here versus the meteorites who arrived from outer space. And by comparing those ratio differences on the paper, drawing lines, he was able to determine the age of the planet for 4.55 billion years, which today had been improved only by 1% in terms of accuracy. But this guy, when he was looking at different isotopes, mainly lead isotopes, he realized there's some anomalies. When he looked at lead on Earth, and long story short, he quickly realized that lead is anthropogenic. Its origin is anthropogenic and coming from that tetraethyl lead that was all spewed in the air by those cars and then precipitated down, basically on everything, and people were taking it into their bodies, from everything, the food, the place they lived, no matter what, that they had contact with. So by 1978, an average American had a lead concentration in their body very close to the level that corresponds to clinical lead poisoning. Right? And this guy was my personal hero, really. He started fighting, he published a number of scientific papers and basically pointed to the problem. Well, we don't have to guess that oil companies, car companies went after him and basically discredited him, and he was thrown out of the National Science Academy. His grant money was taken away, and basically he was accused of falsifying his data, and the counter argument was that this is all natural. That this is not human, he doesn't have human origin, but it's all natural, and he doesn't know what he's doing. So what he did, and this is a really great part of the story, he made a deal with some of the indigenous people leadership in Appalachian Mountains, and they allowed him to undig some of the graves of Indians who were buried in 17th century, 18th century, long before Industrial Revolution. And he did analysis of the remnants, bones, and everything, and basically proved there was no lead in human body back then, and everything comes from the Industrial Revolution. That moment, EPA initiated a program basically eliminating lead from petroleum fuels.
Wow.
He literally, one guy going against the whole goddamn system, saved hundreds of millions of people's lives. Okay.
Wow.
So that curve that you see is that lead concentration of 1 to 5 years old children in the US, since the moment when the regulation was introduced and basically lead was banned in gasoline. And basically nowadays it's non-existent. That poisoning was eliminated. But it was a huge factor that people started looking at alternatives. So before I focus on technology, I would like to give you a little bit of background and a sort of a context of what was happening at the same time. Where different factors came in, because all this and all the pollution related questions were regulated by policy. And you can't forget the fact that policy was a huge stimulus of developing, electrified transportation and moving away from internal combustion engine, both at the federal level as well as on the state level here in California. You remember those initiatives, zero emission vehicles, 100% by 2014. Never happened. However, it was, the direction was set at the time, and then stimulated technology development in this direction. Now, switch slides. So this is the guy exactly the story that I told you, including the determination of the age of the Earth. He's the guy. He's one of the 3 science heroes in all over the history of human race that I have. Hardly anybody knows about it. But in terms of impact of his work, relevant to the reason why we are here today, is enormous. Now, what was happening in the parallel to that, in sort of a science world? So here's another picture of Professor Charles Tobias, who's Hungarian. Actually, he arrived to the United States, shortly after the war. And then he was a professor at UC Berkeley and working closely with Lawrence at the radiation laboratory. He was the first guy, together with his students, who figured out that lithium can be reversibly plated and dissolved in organic solvents, in organic electrolytes. Before that, people never thought that alkaline metals from the first group can be used in any reversible practical device. But the first time he showed that you can take a lithium and it's not going to dissolve like you put a piece of lithium in water and it dissolves instantaneously, but you can preserve it and you can plate it and dissolve in a reversible manner. That was the moment that the whole world understood that lithium has a potential practical application. Now, the other 2 guys from Ford Motor Company in Michigan, Yao and Kumar, in 1967, they published a paper in the journal that you never heard of. Its impact factor probably today would be, 1.5. Okay. And they published a paper in which they demonstrated that a solid sodium beta alumina can conduct sodium ions at room temperature at a comparable level as in liquid. So in other words, ions can move quickly through solid in the same way as they move through liquid. And that was another revelation to the world, that you can build electrochemical devices, including batteries, based on solid state ionics. Materials that conduct ions in and out. You can use them. And that was this paper was an inspiration for everybody else who followed, including Stan Whittingham, including John Goodenough, including Mike Dagger, including all the inventors of lithium-ion or other type of batteries from that moment on. Honestly, I think these two deserve Nobel Prize because everybody else was basically stepping on their shoulders and then following the early work that they were doing. Unfortunately, at the time when the Nobel Prize Committee was considering different names, they were there right now. So they were late. They were coming, trying to recognize them at the time. But without a doubt, without this work, none of this will really happen. The third paper, the third contribution, comes from the Emmanuel Pellet, Professor Pellet from Tel Aviv in Israel, who demonstrated that he can take some of those electrodes, so-called ion intercalation, de-intercalation electrodes, and put it in those organic solvents and then passivate them, in other words, stabilize them, so they can operate in practical devices for a considerable amount of time, which is necessary for practical application. From that moment on, what happened was, I'm going to come back to that later. A little digression for you. I don't know how many of you are chemists or electrochemists okay, what is battery? Okay, battery is a very simple device. It consists of three main things: 2 electrodes and electrolyte. That's pretty much it. As simple as that. One electrode tends to, during charging and discharging, tends to oxidize, and then all species tend to oxidize on the surface, whereas the other one, on the surface of the other one, reduction reactions happen. The redox potentials of these two sets of reactions is different, and the difference between them is the voltage of the battery. That's what we see on the outside. So as the reaction happens on the electrodes, electrons flow through the external circuit, through the load, with your power, and the ions flow the opposite ways, basically closing the circuit, and balancing the charge of the system. So again, without going into physics and stuff, this is conceptually trivial, very simple. This is the electrochemistry course number 1. Okay, this is how you learn. You learn about that in high school. There's nothing really advanced in that. Now, interestingly enough, if you look at there's a book, called Handbook of Batteries. It's about that thick. That size. You probably know that book very well.
Yeah.
There's hundreds of different battery systems, primary, secondary. Primary batteries that you discharge only once. These are the batteries that are used in flashlights. Secondaries that you can reversibly recharge them. There's hundreds of known systems, however, only a few of them made it into commercial applications, as you compare to all the known systems. And the reason for that is that historically, the chemistry or the atomic setup of the battery was and its properties were determined by the application. So I need a battery to do this, and people start looking for, what is the chemical setup of the system that would fulfill the role that the battery would play in practical application. The history kind of changed with lithium-ion, and I'm going to talk about it a little bit. How many of you remember this? Probably everybody.
Oh, yeah. We're all old.
Yes, this was a great success from Sony, a Walkman. Something that Sony made a lot of money and basically brought Sony into the forefront of electronics, portable electronics, at the time. And in most cases, this thing was powered by primary batteries. You build your AA battery, put it in, and operate it. But Sony, when they look at the success of Walkman, they start thinking about this camcorder, another portable device, and then this is the first one they made. And when you look at that box, the gray box on the left, the size of that box is determined by 2 things: the size of the cassette that's inside, the Betamax cassette, and the battery. And that was nickel metal hydride battery at the time. And they quickly realized, well, we can reduce the size of the optics, we can reduce the size of the cassette, but we can't reduce the size of the battery because, this is far more complicated and power hungry than the Walkman. We can't power it with primary batteries because, that will break your budget. We have to reload those batteries every half an hour, and that's impossible. You have to use rechargeable batteries. There was no battery on the market that could fulfill that role of powering more power hungry portable electronics, camcorder in the first place. So if you think of the history, what motivated Sony to start working on lithium ion is this. Not the car, not the grid, not the phone, it was this. So in 1991, first commercial lithium ion battery was released. How does it work? It's again, same simple device, that consists of three main components, two electrodes and the electrolyte in between. Electrons move through the external circuit, ions move through the electrolyte. The difference here is that the lithium-ion battery is made of so-called intercalation materials. Going back to that invention by Yao and Kummer, ions moving through the solids. You have crystalline and semi-crystalline materials that can host lithium-ion reversibly in and out. And while you put lithium ion into one electrode, they are being released by the other electrode. And that process can be reversed. And then depending on your charge or discharge of battery, can be repeated hundreds, if not thousands of times. The advantage of that is that the electrolyte is organic. So the potential window, the difference of potentials of both electrodes is far greater than 1.2 volt, which is allowed in aqueous batteries. In this case, it's more than 3 volts. And that immediately increased the energy density of the battery by a factor of 3 to 5. That's what's exactly needed by Sony to power that camcorder at the time. So conceptually, it looks all great. It looks all great. And then when Sony released that battery, it was a great success. And everybody in the electronics industry immediately realized this is it. This is the moment the portable electronics revolution starts. Because all of a sudden I have a power source that can power the phone and everything else. And since then, the world has changed from you carrying no batteries in your bag and pocket into a world in which you carry at least 2 batteries in your pocket today. Everybody. Okay? Rechargeable battery. That's how the world has changed in the last since 1991 when the first Sony battery was released. Now, so this diagram shows, in terms of energy density. So there's 2 ways you can look at the energy density, how much energy you can pack in a battery. One is specific energy density, which is watt hours per kilogram, meaning, how heavy the battery becomes, how much energy you can store by unit of mass. And the other one is volumetric energy density, how much energy you can store by the unit of volume. When you look at cars, volume matters more than weight. You have a very limited space. Okay? When it looks at the space application, for example, mass matters. Because every pound costs what, $20,000 to shoot up in the lower orbit. For portable electronics, I would say volume, because there's tendency of making them smaller, but those devices become more and more multifunctional, meaning more energy is needed. So it's probably the curve goes right in between, right in between. You need both, smaller mass and smaller volume. Now, so if you look at the history of lithium ion, I mean, this is just a reminder. It's been more than 200 years.
Ile zaraz?
My też, ale później.
Okay. All right. So it's been a long time. So what I reflect on is just relatively recent development. But if you go back to the lithium isolation discovery, it's more than 200 years. But if you look at the battery itself, how it developed over this time, not just lithium, but all of it, in terms of energy density, which is the primary parameter by which you measure them, it's not even close to what, for example, semiconductor industry has achieved, the Moore's law and everything. I mean, that curve is super steep as compared to the progress, that's been made in batteries. So this is super, super slow as other leading branches of industry, which tells you also how difficult it is. The story sounds good. It seems to be natural and easy, but it takes decades, to develop especially practical functional systems, battery systems from those breakthrough discoveries that I mentioned in mine.
So the vertical is energy density.
They're both.
Yeah, they're both. This is more like a kind of parameter, universal parameter of battery performance. So energy density is definitely one. Now, so look on the left side of the screen. So this is how a typical, 3 amp hour battery, lithium-ion battery looks like, 18650, which basically tells you about the dimensions. 18 millimeters diameter, and 35, 65, yes, 65 millimeters length. That's sort of a industry standard in this. And if you look inside, and the way it's made is basically a very simple device, from a sort of a design point of view, in which you have powders of the electroactive materials mixed with some conductive additives and polymeric type of binder, which are cast dotted blade on metallic current collectors, either aluminum or copper. And basically, these two are assembled together, rolled into a roll, put in a can, filled with the electrolyte. That's it. So, however, if you look at the in greater detail into the how the electrode operates, which involves ions moving in and electrons moving in and out, and the interaction between the active and passive components of the electrode is a quite complicated process, which has to be carefully optimized, by any battery manufacturer, regardless of the chemistry. If you open it up even more, and you look at the nano scale or angstrom scale, the TM picture, the transmission electron microscope picture on the right, shows you, crystal lattice, thin films on the surface, and the pointing at the multitude of processes that happen at the interface between active electrode material and the electrolyte, as well as in the bulk, which all have to be carefully optimized and synchronized. In other words, what I'm trying to say, however, going back to the manufacturing technique, you combine, in today's state-of-the-art batteries, still you combine like 21st century material science, absolutely, with 19th century manufacturing. Which is, a lot of that is based on purely empirical approach, trial and error approach. So, and that the gap is still huge. It's still huge. So, what happens since 1991, when Sony developed that battery, for camcorders. Since then, the composition of batteries have changed quite a bit. The new materials, that came into picture. I'm not going to spend too much time explaining. They're all transition metal oxide-based type of materials, and graphite mainly as one of the electrodes. The trend now is to replace graphite with metallic lithium, or even no lithium, metallic lithium, but metallic lithium is sort of an anode, which gives much higher energy density. And the push is put more energy into, any volume or any mass of the battery. We want more miles in the car. People are thinking of putting battery on a plane, not to mention batteries on satellites and other things. Portable electronics, the same. So there's a same effort that's still ongoing, has been going for more than half a century, where material scientists in particular are looking at the different classes of materials, trying to find the one that's going to take more lithium in, store more energy at higher voltage, and that will increase the energy density. Now, there's also increased interest in manufacturing as well. I mean, many people realize that the progress in battery, increasing energy density, can be also achieved not through better materials, but through better manufacturing. If you eliminate plastic materials, you through rational or non-empirical design, that energy density parameters can be also, greatly increased. So it seems like the world of battery making today is more balanced than it used to be, a few tens years ago. Now, another important point that I'd like to make: if you look at the battery, and it's a chemical device, okay, in which charge transfer, electrons go in and out, ions go in and out, and these processes, if you look at all processes that happen in battery, they span across multiple time domains, from ultra fast phenomena that happen at the electrode interface, for example, that go into the picosecond, basic charge transfer, to the diffusion and everything else, and degradation that happens over the years. Okay, battery degrades. You're looking at a device, that goes across, in its operation goes across several time domains. The same with if you look at the length scale of the processes that happen there, from the individual phenomena, single phenomena that happen locally on the action scale, to the battery devices like for the grid application today, which have tens of meters size battery packs. So all these are important factors when you determine the parameters of the of the battery, as well as its performance and lifetime. Why am I mentioning that? This is what happened to all rechargeable high energy batteries. No matter what you do, they all fail, and they're all going to fail. There's no battery that is going to last forever. And the reason for that is one and very simple. Those are thermodynamically unstable devices. The moment you assemble them, they start degrading. There's nothing you can do to stop. It's like, living organisms like us. We're aging. That's it. There's nothing we can do about that. The only thing we can do about this, there's nothing that we can do about thermodynamics and entropy and everything, but we can slow it down by controlling the kinetics of processes, by taking a better control of kinetics of this aging phenomena. That's why I like to compare it with the living organism, because this is exactly what happened with living organisms. If you take care of yourself very well,
Right.
the kinetics, you can live longer a little bit. That's true. Okay. But the batteries, it is true. But if you really do control those detrimental phenomena that happen, it must happen, to the point that you suppress them really well, you can extend the lifetime of the battery to match the requirement of the application that those batteries go in. A good electrochemical process that, maybe compared with that is corrosion. Metals like iron corrode, and if you take good care, you can slow down the corrosion to the point that you can build a bridge out of that, or you can do something else. Same happened on a far more complex level, with these systems, and understanding what is happening inside and how this happening is one of the key factors. And that is the schematics of what I just showed. In high energy batteries, at least one electrode resides outside of the stability window of the electrolyte. In other words, the electrode gets in contact with the electrolyte and it either reduces it or oxidizes it. And the only way that you can prevent that the whole electrolyte is consumed in this process is that the electrode passivates on the surface, like in corrosion. You build a passive layer, and those processes slow down at a very low rate, and the battery can, the main operation of the battery can be guaranteed over a long period of time. That film that protects the electrode, which was a turning point in the development of lithium-ion battery, is a complex. It's a simple film, but 45 years after, and I think 120,000 papers, scientific papers, published on the matter, we still don't really know what's going on there. So part of my job, and then the lab is doing, is trying to figure out what is happening and how to produce that film, not in a what's called empirical way, in which the battery goes through a formation process in which you slowly cycle it initially, and the film grows and then protects the electrode, and the battery is ready for the application. But something that, if you understand it really well and how to protect the surface and preserve the function, you can make it artificially right up front, and you can save the money and time, basically skipping the whole formation process and make a battery that is ready for prime time right off the assembly line. Now, having said that, this is a sample for you. I like to confuse people with this slide. It's like, the schematic of the reactions that happen, and I can guarantee you they're not all of them. And that's how complex this whole process is, and which corresponds to like organic synthesis in which you always get, the whole spectrum of products. In this case, this whole organic chemistry is driven by electrochemical potential. But deciphering and deconvoluting all these processes and understanding what's going on, what matters, what doesn't matter, is in some way essential for the success of the systems. That's what we do in the labs a lot, both on the theory side as well as on the experimental side. I'm not going to go into details. This is sort of a history of showing you in a artist depiction way, how the understanding and sort of visualizing what the film is really, to the history of those studies, going back to the 1970s until now. And I often joke that, all the unknown remains, still remain all what changes the graphic depiction and the coloration of these pictures. But honestly, we're still far away from understanding it better. Why is this important? Because it's not just the lithium-ion battery problem or requirement, it's any high energy battery, rechargeable battery requirement. So that understanding or the way of figuring out, how to replace that empirically grown film with artificial one could have quite serious implications for many other systems that are being considered today. What is being considered? So this is a copy of a so-called Ragon plot that shows specific powers versus specific energy of different battery systems. So you see lithium-ion batteries here, you see supercapacitors, you see lithium-sulfur systems that some people work on, magnesium batteries, lithium air or metal air batteries altogether. So there's many systems that people are super busy now, and some of them show some promise, and some of them enter into commercialization stages. None of these batteries is going to be universally applicable for any type of commercial applications. They will have a specific use depending on, on their characteristics. But where they're going to go to is going to be electronics for sure. And this is not going to stop. It's going to enhance interfacing hardware of the living organism is going to happen in the next few years. Musk and one of his companies working on that right now. That will need power of a completely different type. Transportation, if you ask me, given the policy, technology advancement, and then all the environmental concerns, that transition is not going to stop. The question is from sort of like a combustion engine into electric. It's not going to stop. The question is how long it's going to take. And that is a question about infrastructure. And more importantly, is the question about the grid. Again, going back to my early slide showing the grid, invented by Edison, Tesla, and stuff. This is old, as you look at in the world, the renewables, being brought in, and new power, new energy sinks like data centers. You've heard that Microsoft bought the nuclear power plant, 3 Mile Line nuclear power plant, and they're going to recommission it to power the data centers. So the picture has changed quite dramatically, and energy storage is going to play most likely a very important role in grid at different stages. Behind the meter, before meter, small units versus large units is going to be all over the place. The success of that transition within the grid will be driving the transition in transportation in other domains and vice versa. So it's again a complex world in which those parameters is going to, interact with each other and move it forward. But I think that we are over the critical point or critical mass of factors that make it unstoppable at this time. So I come from Department of Energy Research Lab. This is what DOE is doing nowadays. And they started a big initiative called Energy Storage Grand Challenge Roadmap. There's a report that was published 4 years ago, I think. You can download it from the web. If you really want to get 2 main goals from that report, where the battery world is going nowadays, is the cost. The cost is primary factor in which, many industries is, they really look as a critical driver. And especially for the grid, when you look at the scale, large scale batteries, the cost has to go down by orders of magnitude. And the target is 2030. What, 5 years left only? That's not much. For transportation, the cost of the lithium battery pack for a car with 300-mile range is supposed to go down 44% from 140, which was, I think, the price 4 years ago. Now it's lower than that. A little bit. But they really want to bring it down to 80, which is going to be really close to a standard nickel metal hydride battery, which is an aqueous-based system in terms of cost. And that is a huge advancement if you think that the moment when lithium-ion battery was commercialized, its cost was $1,000 per kilowatt hour. $1,000. So the cost is now down 10x. Yeah. And that trend is still maintained, and that's what a lot of effort is going on, both on research and technology development side. And with that, I'd like to stop. I'm happy to answer any questions or explanations. Thank you.
Thank you. Go ahead.
One is materials, availability of materials. Lithium, we know what's going on. We know that we need more storage, more batteries, right? Is there enough materials, which we are thinking about?
Zoomers, can you hear this?
It's not like silicon, which is abundant.
Yeah, it's a very good question. I should have mentioned that. It is actually it's very much included in that grand challenge roadmap that all the supply chains have to be secure. Lithium is a good example. I mean, lithium is is all over the planet. There's no shortage of lithium. If you look at the amount of lithium that's present, there's huge amount of lithium in the United States, including particularly in California. The difference is, though, currently most of lithium comes from two places in the world. One from Australia, when they mine ore and they ship it all to China, when Chinese extract it using acid and thermal techniques. And the other comes from Chile and Bolivia, I believe, when there's subterranean brines that they really pump up and they dry them in the sun and basically process that into lithium carbonate. There's lots of lithium in California in two places, Salton Sea, down below, and northern part of California, close to the border with Nevada. There are two different geological deposits. Now, Salton Sea is hot brine from geothermal source. It's basically the geothermal power stations that were built at Salton Sea are being powered by those lithium. Well, they're not super rich, but lithium-containing brines. And then in the northern California, there's geological deposits 5 miles deep underground. None of these deposits can be touched with traditional mining techniques. So it's not the matter of shortage of lithium per se. It's the matter of shortage of technology, proper mining technology that can be cost competitive with the state of the art.
Question of time.
Yes, and then the permitting and everything else. What people could have done, could do 50 years ago in terms of mining here in Nevada, nobody is going to issue a permit today because of the environmental concerns. So the technology not only has to be cost effective, but it has to be environmentally friendly. You can't do what, for example, is happening in China when those acid leaching processes basically create literally hundreds of miles of dystopian landscape, when the life will basically cease to exist because it's being dumped, out in the environment. That can't happen here. So that's the challenge and the call for both scientists and technologists to address, and then bring back that kind of manufacturing based on modern technologies for the States, including battery materials.
But we are going to
Thank you.
acquire Greenland, right? And there is a lot of lithium there.
Well, yeah, sleep under the snow or the ice.
But the second question, I just want to,
That's where global warming
Dominate.
plays into our hands.
I don't want to be blamed that, because of lithium-ion batteries, we have to acquire Greenland now, but then, but what I'm saying is that there's plenty of lithium, not necessarily in Greenland, right there that we can get, but we need some technology solutions.
With respect to the Department of Energy challenges, do you think that the politics will shift these challenges towards, away from renewable and battery type of things into
Okay.
drill, baby, drill?
Okay.
Okay.
Well, I don't know how many of you have listened to the hearing of the new Secretary of Energy. It happened a couple of days ago.
No?
It's a good, well, I would recommend you to do two things. One is listen to the
What?
hearing in front of Senate committee, the Energy Committee. And the second is listen to the podcast he posted on his LinkedIn site from 1 year ago.
Huh.
Two different people.
And the same name?
He even looks the same. He even looks the same. But then
All right,
two different messages.
Just different slides.
thank you.
So
Thank you.
if you're interested in what's coming, just go ahead and listen to that.
Thank you very much, Robert.